Okay, so today we are going to take a look at binding energy in the world of nuclear forces and modern physics. So, binding energy, in short, is simply the amount of energy actually holding a nucleus together. Okay, and here's how we can kind of look at it and see just where this binding energy comes from. If we take a fairly common element like helium, let's look at the mass of helium here. We'll write this as the mass of helium, and then we'll say, helium's He 4 2. There's 4 for the atomic mass number, 2 for the atomic number itself, 2 protons, 2 neutrons. And if we look this up in a table, and for our class, we use the Giancoli, the holy textbook, 6th edition. If you go into a back table, you can find the mass numbers for all of this stuff. And for helium, this is 4 point, in its decimal time, 002603 atomic mass units, because those AMUs are what we're starting to use now. Now, as we mentioned, the helium is made up of 2 protons, 2 more neutrons, and then, technically there's some electrons in there as well. So let's add up all of the mass from the 2 neutrons plus the 2 protons. And even though they're really small, like so much smaller than the protons and neutrons, they actually don't matter. Let's just be complete, and let's actually add in the electrons as well, okay? If we do this, and if you forget what these values are in atomic mass units, go back and check out an old video that we have to see them for the atomic mass unit idea. The 2 masses of the neutron, so we'll call it Mn, are equal to 2.017330 AMUs. And if we add that to the 2 protons and the 2 electrons, those electrons and protons added together are 2.015650. And remember, those electrons are so small, they're like only down here, adding to like the little end. We really don't need to concern ourselves with them on a normal basis, but just for completeness, like I said. And these are also in atomic mass units. Now, if we go back into first grade and we add up all of our columns here, we get the following. We get 4.032980 atomic mass units, which 4.03, wait a second. Why is this number bigger than this one? This is the actual textbook. This is what helium's mass is. It's what helium's mass actually is. This is correct. This is like the actual mass. But down here, this is what the math should be in theory. What? Why is this theoretical mass larger than what we actually see? Well, if we recall, a brilliant physicist said E equals mc squared. And we know that there's more to this equation, but we're not dealing with photons of light here or their momentum. So if we just take and think about the idea of mass energy, them being equivalent, then the missing mass that we have for our actual recorded, there's mass missing here, right? There's some missing mass. That missing mass is equivalent to our binding energy. That missing that mass that we have has been converted into energy to hold the nucleus together. So if we subtract these 2 values here, the theoretical mass from our accepted value, what we'll see here is, and we'll just write this out for completeness, 4.032980 AMUs, that's our theoretical, minus the actual 4.002603 AMUs. We find that there's a mass difference here of 0.030377 atomic mass units. This missing mass right here, this is the missing mass. This is equal to the binding energy. That is the binding energy there. That is the actual energy holding these nucleons, these protons and neutrons in the nucleus, together. Okay? if we wanted to figure out how much energy that actually is, because right now it's still in like a mass unit, it's in an atomic mass unit here. How much energy is that actually? We actually have a really easy way to convert from AMUs into energy. If you recall, there's this nifty number, 931.5 mega electron volts, that comes up. It turns out that mega electron volts divided by c squared is equivalent to mass, and this means that if we take this idea of an AMU, we can say that there's 931.5 mega electron volts in one atomic mass unit. It ends up working out the very similar way in terms of how numbers go around. So all we have to do is simply take this quantity here, our missing mass, the 0.030377 atomic mass units, multiply it by the 931.5 MeVs for AMUs. The AMUs, wing wing, go away. And we quickly have here a value in terms of energy. And for helium, this is 28.30 mega electron volts. If you wanted to do this per nucleon, like how much binding energy is needed per nucleon, per proton, or per neutron, then you would divide it by the atomic mass number. So in this case, if we took 28.30 MeVs and divided it by 4, because there's 2 protons, 2 neutrons, add them up, that's 4, then we would get a quantity of about 7.1 MeVs per nucleon. Okay? And for nearly every single element, this is how we think about our binding energy, and this is how we think about our binding energy per nucleon. There is one element that's a little weird, though. It is hydrogen. Hydrogen, if we recall, is H11 for a standard non-isotope form, which means it only has a proton, which means it's not bound to anything there. The only real binding energy that exists with hydrogen is the fact that the electron is held in its electron cloud. And we've already talked about this briefly. We know that the energy to remove that electron can be given to us by the equation of negative 13.6 z squared over n squared. And for hydrogen, this z squared is just 1, so we can ignore it. And if we take the differences here, the binding energy of an electron for hydrogen is just the negative 13.6 electron volts. Notice here that this is in electron volts, that electron's very easy to rip out of the hydrogen atom. In terms of the nucleus, though, these protons and neutrons being held together, these are mega electron volts. So vast, vast quantities of energy, larger than just stripping an electron from a hydrogen. Actually splitting the nucleus of an atom is a ton of energy being stored in there. And if you had a clever way to do it, you could get a lot of energy out of this and maybe get something to go and build a little bit of a mushroom cloud yourself. But until then, this is the idea of binding energy. It's where this missing mass is located. We look at our accepted mass from a table in a textbook. We add up what we know should be in there. We added in the electrons here, but you really don't need them. Most of the time you'll see examples where they don't even put that in. Doesn't really matter because it's not in the nucleus. But we just wanted to see, if it was there, where would that mass go? And then we simply take that mass difference, multiply by the 931.5 MeVs, and then if you want to do it per nucleon, divide by that atomic mass number. But for now, this is finished. We'll take another look at an example for this for lithium momentarily. But until next time, adios, and take it easy.